Building printing refers to various technology that use 3D printing as a way to construct buildings. Potential advantages of this process include quicker construction, lower labor costs, and less waste produced. 3D printing at a large scale may be well suited for construction of extraterrestrial structures on the Moon or other planets where environmental conditions are less conducive to human labor-intensive building practices. Developments in additive manufacturing technologies have included attempts to make 3D printers capable of producing structural buildings. History. Related technology development began in the 1960s, with pumped concrete and isocyanate foams. Current technology. Modern development and research have been underway since 2004 to flexibly construct buildings for commercial and private habitation, with built-in plumbing and electrical facilities. In one continuous build, the process uses large 3D printers that would notionally complete the building in approximately 20 hours of printer time. By January 2013, working versions of 3D printing building technology were printing 2 meters of building material per hour, with a follow-on generation of printers proposed to be capable of 3.5 meters per hour, sufficient to complete a building in a week. Derek Koshnevas founded the Contour Crafting project, which demonstrated the basic capability, based on 2 parallel rails, an XY-controlled printing gantry and pressurized concrete tank. Dutch architect Jan-Jaap Ruijsenaars' performative architecture 3D printed building was planned to be built by a partnership of Dutch companies. The house was planned to be built in the end of 2014, but this deadline wasn't met. The companies said that they are still 100% sure the house will be printed. Various approaches to building printing are being researched. 2 of these are contour crafting and D-shape. Other approaches involve direct sintering of inorganic raw materials to build composite ceramic building structures, similar to the approach used with metals in direct metal laser sintering. 3D printed residential buildings in the Netherlands. DUS Architects is 3D printing a 3D printed canal house, together with an international team of partners. The 3D print canal house links science, design, construction and community at an open building site in the heart of Amsterdam. Their aim is to demonstrate how 3D printing could revolutionize construction by increasing efficiency and reducing pollution and waste, and offer new tailor-made housing solutions worldwide. 3D printing could also play a significant role in the quick build of low-cost housing in impoverished areas and those affected by disasters. The 3D print canal house is currently under construction at a canal-side plot in Amsterdam, an open expo site that it is proving to be a popular visitor attraction for the public. At the heart of the site is the Kamer Maker, or room builder, which is essentially a scaled-up version of a tabletop 3D printer. The Kamer Maker prints building blocks from molten bioplastic. This is currently a mix of 80% plant oil reinforced with microfibers. Although this formula is still under development with the project's materials partner Henkel. For reinforcement, the blocks have an internal honeycombed center that can be backfilled with eco-concrete. It also provides space for pipes, wiring and data cables to be installed internally. The building blocks are then used to form component parts that can be slotted together like Lego to create a 4-story, 13-room structure modeled on a traditional Dutch canal house. One of the most distinct design features of the canal house is its geometrically faceted plastic facade. 3D print house building blocks. This gives a contemporary 3D print twist to the traditional canal house silhouette. The ability to print ornamental detailing on demand is a key design benefit of 3D modeling and printing in the building industry. With costly labor-intensive work reduced, custom-designed homes would become more accessible. So what are the main benefits of printing a house? Waste materials are a big problem for the building industry, but with 3D printing only the necessary raw materials are produced for each project. An added bonus is that 3D printer ink can be made from recycled plastic waste. If printing on site, transport costs and CO2 emissions are greatly reduced, as are dust and noise levels. And when the building is no longer needed, it can be shredded and recycled. Another key driver for developing this technology within the construction industry is the growing need for rapidly produced housing. In this respect, 3D printing has the potential to reshape the way in which we build our cities, especially as megacities are on the increase around the globe. The 3D print canal house was the first full-scale construction project of its kind to get off the ground. In just a short space of time, the camera maker has been further developed to increase its production speed by 300%. However, progress has not been swift enough to claim the title of world's first 3D printed house. The Chinese company Winsun has built several houses using large 3D printers, sparing a mixture of quick-drying cement and recycled raw materials. 10 demo houses were built in 24 hours, each costing $5,000. Dutch and Chinese demonstration projects are slowly constructing 3D printed buildings, using the effort to educate the public to the possibilities of the new plant-based building technology and to spur greater innovation in 3D printing of residential buildings. Extraterrestrial printed structures. The printing of buildings has been proposed as a particularly useful technology for constructing off-Earth habitats, such as habitats on the Moon or Mars. As of 2013, update. The European Space Agency was working with London-based Foster Plus partners to examine the potential of printing lunar bases using regular 3D printing technology. The architectural firm proposed a building construction 3D printer technology in January 2013 that would use lunar regolith raw materials to produce lunar building structures while using enclosed inflatable habitats for housing the human occupants inside the hard-shell printed lunar structures. Overall, these habitats would require only 10% of the structural mass to be transported from Earth, while using local lunar materials for the other 90% of the structural mass. The dome-shaped structures would be a weight-bearing catenary form, with structural support provided by a closed-cell structure, reminiscent of bird bones. In this conception, printed lunar soil will provide both radiation and temperature insulation for the lunar occupants. The building technology mixes lunar material with magnesium oxide, which will turn the moon stuff into a pulp that can be sprayed to form the block. When a binding salt is applied that converts this material into a stone-like solid, a type of sulfur concrete is also envisioned. Tests of 3D printing of an architectural structure with simulated lunar material have been completed, using a large vacuum chamber in a terrestrial lab. The technique involves injecting the binding liquid under the surface of the regolith with a 3D printer nozzle, which in tests trap 2 mm scale droplets under the surface via capillary forces. The printer used was the D-shape. A variety of lunar infrastructure elements have been conceived for 3D structural printing, including landing pads, blast protection walls, roads, hangars and fuel storage. In early 2014, NASA funded a small study at the University of Southern California to further develop the contour crafting 3D printing technique. Potential applications of this technology include constructing lunar structures of a material that could consist of up to 90% lunar material, with only 10% of the material requiring transport from Earth. NASA is also looking at a different technique that would involve the sintering of lunar dust using low-power microwave energy. The lunar material would be bound by heating to 1,200 to 1,500 degrees Celsius, somewhat below the melting point. In order to fuse the nanoparticle dust into a solid block that is ceramic-like, and would not require the transport of a binder material from Earth as required by the Foster Plus partners, contour crafting, and D-shape approaches to extraterrestrial building printing. One specific proposed plan for building a lunar base using this technique would be called Sinterhab, and would utilize the JPL six-legged athlete robot to autonomously or telerobotically build lunar structures.